we're talking about the motion of rigid objects. So I'm starting off with the simplest rigid object that you could imagine. I'm gonna give you this code. Okay, so this is two masses connected by a very, very stiff spring, and so that spring doesn't really move that much, but it makes these two masses move in the pattern that we see. So let me run it again, and then I'll show you the code and explain to you, but I'm not going to go over the code because we're going to modify the code, but I'm going to explain the code. And we're going to talk about this, the rotations of rigid objects, for a simple case, and then a slightly more complicated case, and we're going to do a whole bunch of stuff. I'm not going to derive these things. I'm just going to show you that they are indeed true. Okay, so there's that. So the way this code works is I have two masses. I'm calling them mass A and mass B, and they have a position and they have an initial momentum. And then right here I have the spring. So the spring force just takes the initial position of the two and says, okay, well, if it stretches further, then it's going to pull the two together. If it compresses, it's going to push them apart. And that keeps them at a set distance because the spring constant is super high. What is my 2,000 newtons per meter? Okay. So, and then all I do is go through, I calculate the relative positions, I use that to calculate the force, there's no gravity, and then I use that to update the momentum and update the position, and there you go, everything's great. Okay, the first thing I want to do is to change this motion to the center of mass. I want to calculate the center of mass, and I want to set the total momentum to 0. So let me show you on the board how we find the center of mass for this situation. I'm going to put a point there, and then we're going to let the whole thing rotate about that center of mass by setting the total momentum equal to 0. Okay, so if we switch up here to the board, here we are. So I have here two masses, and they have some position. Let's just say, I don't need these arrows. Let's say this is R1, the vector R1, and this is the vector R2. Then I can find the location of the center of mass. I'll call that R-com. Com stands for center of mass. So R-com is going to be equal to, in this case, well, in general, it's the sum over I of mi Ri over the total mass. I'll just call that total m. So here, that's pretty easy, right? I can just say that's equal to R, I called these A, I called them A and B. MA plus MB RB over MA plus MB. And that's going to be a vector location of the center mass. Now, if I want the center of mass to be stationary, then I need the total momentum to be 0. So let's suppose that this has a momentum. I'm going to have it move up with, I'm going to switch it to A, PA, and this would be PB. I can make that whatever I want, right? What I need to make is this have a momentum that's equal and opposite, such that PA plus PB is equal to 0. So if the total momentum is 0, then the center of mass will be stationary. Now, finally, I'm going to tell you the last thing I want to do. I want to do two things. I want to calculate the kinetic energy two different ways. So first, I can say the kinetic energy is 1/2 ma va squared plus 1/2 mb vb squared. That's just the kinetic energy formula, right? Both of the masses have velocity, both of them have mass, both of them have kinetic energy. Now, I'm going to actually plot this, but we can also write this as PA squared over 2MA plus PB squared over 2MB. Right? That's a little bit easier way to do it, and these are magnitudes of momentum since I have the momentums. If you divide by the mass, that's fine. Finally, what I want to do is to take this vector right here, I'll call that RB, RA, and I can calculate the kinetic energy of a rigid object as 1/2 I omega squared. So omega is the angular velocity. We have to find that. I is the moment of inertia about a fixed axis. We have to find that too. So omega is just going to be V over R, right? So I can take the velocity of this one and divide by its radius, the distance from the point of rotation. Now, this works only in a certain situation. You can't always do that. You're going to see later that we can't do this. Do I have chalk all over me? That's fine. I still have my mic though. So I can calculate the angular velocity. These two should have the same angular velocity, and we'll check that. For the moment of inertia about a fixed axis, it's going to be the sum over I, mi ri squared. So r is the distance from the axis of rotation. So this is in a flat plane, and the axis of rotation is in the z direction, so it shouldn't be too hard. Okay, so we have a bunch of stuff, but the main thing is I want to calculate those two moments, those two kinetic energies. Let's jump back to the code and just change it. Let's just change the code so that we can do that. So the first thing I'm going to do down here before the loop, I'm going to calculate the center of mass. I'm going to say rcom is equal to, this would just be parentheses, mass A dot m times mass A dot POS, which is the vector location of mass A, plus mass B dot m times mass B dot POS, and then I need to divide that by mass A dot m plus mass B dot m. So that's the vector location. Now I'm going to put a sphere there. I'm going to call it com for center of mass, and it's a sphere with a location POS equals rcom. And then the radius, I'm just looking at the radiuses of these other ones. 0.0, let's make it a little bit smaller. Radius is 0.05. Okay, now down here, the other thing I want to do is to make the total momentum 0. So right here, I started off with one of the momentums at some value and the other one at 0. So I can just change that. So I already had that code in here. So now the momentum of mass B is the opposite of mass A, so that the total momentum is 0. Let's just run this, and then we can do some calculations. Oh, I must have misspelled radius. Sphere, radius is 0.05. Sphere, I spelled it right. Oh, 0.05. 0.005. There. Okay. So there's my center mass, and then the two objects are rotating around that center mass. Now, I'm going to calculate their actual kinetic energy. Do I have to plot it? I'm just going to calculate it, just because we have a bunch of other stuff to do. So let's calculate the kinetic energy two ways. So I'm going to first call this first way K1. It's going to be 0.5 times mass A times mass A dot m times, oh, I'm sorry, we did momentum. So it's going to be magnitude of mass A dot P squared divided by 2 times mass A dot m. That's P squared over 2m. And then the other one is going to be plus magnitude of mass B dot P squared divided by 2 times mass B dot m. So that's P squared over 2m. Now for the other one, I need to calculate I. So let's calculate I. I is going to be equal to the distance from the point of rotation squared. So I'm going to make two variables. I'm going to say RA is going to be equal to mass A dot POS minus rcom, right? Because now I'm going from the center mass to that location. And then RB is going to be mass B dot POS minus rcom. So now the moment of inertia, I, about a fixed axis, I is going to be mass A dot m times mag RA squared, right? Because I can't square vectors, so you have to take the magnitude. And this is indeed the distance to the axis of rotation because my stuff's in the xy plane. That's an important point. Plus mass B dot m times mag RB squared. So that's I. Now let's just calculate omega, and I'm going to print out omega just to make sure I can do it two ways. Let's see, omega equals, I said it was the velocity divided by the radius. Okay, so I can do that, but my radius and my velocity are both vectors. So let's just do magnitude. Let's just do the magnitude. We already know the direction, and it doesn't really matter about anything else. So I'm going to say the magnitude of mass A dot P divided by mass A dot M. That's the velocity. And then divide that by the magnitude of RA. And let's print that just to check, right? And then I'm going to do it again. I can just copy this and paste it and do it for mass B. They should have the same angular velocity. I'm just going to change these to B's, B, B. Okay, let's run that and see what happens. All we did was calculate the angular velocity. Well, that's what we're printing. And there we go, 1.5. So it is indeed 1.5, and I actually set that at the beginning, so that does indeed work. So now we can print everything out, right? So I don't need to print that. I don't need to do all this stuff. I can delete that. They're both the same. So now K2 is going to be 0.5 times I times omega squared. And now let's print them. Print K1. It's going to be K1. I'll leave off the units. Print K2 equals, I'll leave off the units K2. What am I doing here? Let's just think, what am I doing? I'm trying to show you that we can deal with a rigid object as individual masses or as a rigid object and get the same thing. And then I don't care about that. Same kinetic energy. Kinetic energy is the same either way. Okay, now let's calculate the angular momentum. Jump back to the board for a second. And we're doing this in 2D, right? It's going to be easy. And then we're going to do it in 3D, and it's going to be fun. So we can calculate the angular momentum two ways. L is going to be RA cross PA. That's the angular momentum of a point, plus RB cross PB, the angular momentum of a point. I can treat them as point masses, or I can say L is I omega. Now, in this case, I'm writing that as a scalar because my angular velocity was a scalar. I is a scalar. I'm just going to write it as that. So let's calculate both these ways and see if they're the same thing. We could plot them if we wanted to, but we don't need to. I'm just going to calculate them. We could assume that they're constant over time. They are indeed. I'll plot them. Actually, I will plot them. Let's plot the two angular momentums. So do I have two graphs up here? F1, let's put up another graph. F2 equals G curve, color equals color dot red. And then I'm going to calculate these two things. So I'm just going to do it down here in the loop. I'm going to calculate the angular momentums. So I'll calculate L1. L1 is going to be R cross P. So it's cross. Oh, I need to recalculate RA. I need to recalculate RB. So let's calculate those. RA is going to be mass A dot POS minus RCOM. I need to recalculate RCOM too, technically, but I don't need to because it didn't move. If it did move, you could recalculate that. RB equals mass B dot POS minus RCOM. So L1 as point mass is going to be R cross P. So RA mass A dot P, that's the first one, right? And then I have to add in the angular momentum of the other one, cross RB mass B dot P. Now the other way I can do this is to do I omega. So I didn't change, right? It just depends on R and the mass. And omega didn't change. So I don't need to recalculate that. Let's just do that. L2 is going to be equal to I times omega. Now let's plot them. F1 dot plot. I'm going to plot this as L1 dot z. So L1 I calculated as an actual vector. So I'm just going to use the z component. And then L2 is not an actual vector. F2 dot plot T L2. Let's just see if they give the same thing. And they don't because I had an arrow. Mass B. What? I don't have mass B. Oh, NAS B. Where did I say NAS B? NAS. Look at that. It looks like an M. That's strange because I'm usually a pretty good typer. Okay, so there we go. And you see that we have different values. So I have 6 times 10 to the negative third and negative. Okay, they're the same. One's just positive, one's negative. Okay, but they agree because this is the way I calculated it. The way it's rotating, it's actually in the negative z direction. I think we're good here. I think we're good. So we've shown that if we define the moment of inertia as I, the sum over I, mi ri squared, then I can write the angular momentum as I omega. I can write the kinetic energy as 1/2 I omega squared. Well, if we can do that for 2 rotating objects, we could do that for 3 rotating objects. So let's switch to another program and look at 3 rotating objects. It'll be a lot of fun. Okay, I think, did I get this? Okay, I think I got it. Okay, so I'm switching over here. Yeah, here's my 3-mass rotator program. I'm just going to run it. And I have some extra stuff in here, but it's basically the same thing. So I've already set the center mass to be stationary, and I have 3 objects. They're all connected by springs, and they're rotating in a very well-behaved fashion like this. So you can see it's all in a flat plane, and that's kind of cool. I think it's cool. Okay, so the first thing I want to do is do the same thing. I want to calculate the angular momentum 2 different ways. I want to calculate the angular momentum with respect to the point masses, r cross p plus r cross p plus r cross p, and then I want to do it as I omega. So I need to calculate I. Okay. So in this case, I did give omega as a vector. I set omega as a vector, and I use that to give the initial velocities of the things. So I just did that. Okay. But that also means that the whole thing rotates fine. I do need to calculate the center of mass because it's not at the origin. So let's calculate the center mass, which I did right here, RCOM. Let's just print that. I thought I had to calculate the center mass in order to get the momentums correct because I had to have their velocity relative to the center mass. So I have their center mass. That's fine. RC is the center mass. That's fine. And it is stationary. So I don't need to recalculate that. One thing you'll notice here is that in order to do that, I put masses as a list of objects. Mass A, mass B, mass C, and it just made it easier for other things, but it doesn't, just so I could pass that to the function. Okay, so I have that. I want to just go ahead and do the same plot. I want to plot LZ 2 different ways. So I'm going to say I omega. Omega is now a vector, so I need to calculate I. It doesn't change, so I'm going to calculate it once. I is going to be, I do need those 2 vectors. So I need RA is going to be equal to, let's do that down. Let's just do it all down here, every single time. Calculate stuff. So I'm going to calculate RA is going to be mass A dot POS minus, what did I call it, RC? I called it RC in this case. Yep, RC. RB is mass B dot POS minus RC. And then RC is mass C dot POS minus RC. And then I can use that to calculate the moment of inertia. I equals mass A dot M times RA mag, RA squared, plus mass B dot M times mag, RB squared, and then plus mass C dot M times mag RC C squared. So that's my moment of inertia. Now I can calculate the angular momentum. I called it L2. L2 is going to be I times omega. Omega is a vector, so I'm going to get this as a vector this time. Now let's calculate the other angular momentum. It's going to be cross RA mass A dot P plus cross RB mass B dot P plus cross mass C dot M time, comma, mass, no, RC mass C dot P. So now I have 2 angular momentums. Let's go ahead and plot those. F1 dot plot is going to be TL1 dot Z. F2 dot plot is TL2 dot Z. Let's run it and see what kind of damage we did here. I did some damage. F1. Okay, up here, I just did this. Let's just delete all that stuff. I don't need it. F1 equals G-curve, color equals color.blue. You can see I reuse this program. F2 equals G-curve, color equals color.red. Okay. So there we get the two angular momentums. They're not identical, but they're very identical-ish, right? So this is going from 875 times 10 to the negative fifth to 875 times 10 to the negative fifth of 0.5. So it's a very, very tiny window, and one of them keeps oscillating because the springs are actually moving the thing. So in the R cross P version, we actually get some variations in the angular momentum, and that's fine, okay? So, but it does indeed work. Now for the fun part. What happens if we change the angular velocity? So instead of being in the z direction, I give it an x component. I'm going to run it and see what happens. Look at that. It rotates funny. It rotates in a way that is clear the angular momentum and the angular velocity, well, the angular velocity is not constant, okay? So this still gives me some weird values, and that's fine. But the angular momentum and the angular velocity are not in the same direction. The angular momentum has to be constant because there's no torque on the system, but the angular velocity is not constant. So what we need to do is to use a different way to calculate the moment of inertia, and that's where we get the moment of inertia tensor. So what I want to do is to calculate the moment of inertia tensor and calculate the angular velocity or calculate the angular momentum using that, and then compare that to R cross P. I'm going to print it. I'm not going to run it because every time it rotates, my moment of inertia changes. There's a way to deal with that, but I'll handle that later. So let's go back to the board and talk about how you would deal with these three mass systems. And the key thing here is that we do not have a fixed axis of rotation. So in this case, I can still have L as the sum of Ri cross Pi. That's still true. But then the other way is to say L is I omega, but I is the moment of inertia tensor. So I looks like this. I xx, I xy, I xz, I yx, I yy, I yz, I zx, I zy, I z z. So we're going to need to calculate all those elements, and we can do that. I x x is going to be m, the sum, over I, mi times, I'm just going to use x and y and z values. This is going to be yi squared plus zi squared. So this is the moment of inertia about the x-axis, and so we don't use the x values, right? We use the distance of the x values, and that is the same thing as what we had before. Now, that would be the same thing for yy and zz. Yy would just be x squared, zz would be x squared, y squared. Now, for the off-diagonal elements, x, y, it's going to be negative the sum over I, mi, x, I, yi. So I just take the product of those two. So I need to calculate those for all my masses, and then I can get this, this matrix here. Now, I'm using Web v Python. I hope you know that. And in Web v Python, there are no ways to operate matrices with a vector. So I'm going to actually write my moment of inertia, I, as the list ix, iy, iz. And where ix is the vector, it's the vector ixx, ixy, ixz. So if I do that and then I operate this, I want to operate it with a vector omega. What I need to do is to say this is going to be the vector ix dot omega, iy dot omega, iz dot omega. And that would be, yeah, that was true. And that would be my angular momentum L. So that's not I anymore. Okay. Okay, so we got a bunch of stuff to do. And I'm going to do this just once. Like I said, I'm going to do it once, and then we're going to calculate the I matrix, and then I'm going to operate it on the angular velocity, and I'm going to compare it to that. Let's get the first part done first. Oh, look, I got my thumb thing back. Let's get the first thing part done first, L1. That'll be easier, and then we'll do the other stuff. So again, we're not running the loop. It doesn't really matter. So I'm going to do this all at the top. So I do need this thing that I did before. I'm going to put right down here before that. I do need my RA, RB, RC. So let's just go ahead and get those out of the way. RA is mass A dot POS minus RCOM. RB is mass B dot POS minus RC. And then RC equals mass C dot POS minus RC. And then I'm going to go ahead and calculate L1. L1 is going to be cross RA mass A dot P plus cross RB mass B dot P plus cross mass C dot, no, RC. I did that before. RC mass C dot P. So I'm done with the first part, angular momentum. Now I need to calculate the moment of inertia. And so this is going to be a little bit tough, right? So I want to calculate Ix, Iy, Iz. Let's just do this, okay? Yeah. So I already have my masses as a list. So let's do this. Let's do this. Ix equals vector 0, 0, 0. I'm going to add it to this. Iy is vector 0, 0, 0. I'm going to add stuff to that. Iz is vector 0, 0, 0. So I have those to begin with. Now I'm going to say for I in length, range, masses. No, I don't even need to do that. Can I do? I think I can just do for mm in masses. Yeah, I think I can. Mm in masses. So remember, masses is a list of all my spheres. So I'm going to call each one of them it would be nice. So now what I want to do is go through and calculate my Ix components and add it to that. So I'm going to say Ix is going to be equal to Ix plus the vector. This is kind of weird, right? But in the x direction, I'm going to take the mass, which is mm.m, times Ix, the x component's going to be times mm dot oh, I do need to do, I need to redo these R's. RA. Let's just do this I want to do it the times, yeah, I can't do that. Well, let's just do, let's just do it the long way. Okay, Ix is going to be equal to, let's just calculate them all separately. Let's do it the long way. Ixx is going to be the sum, so it's, oh gosh. I guess I can redo that in here. For mm in masses. Okay, so I have that. Let's just recalculate RA, RB, RC for mm. So RA is going to be mm.POS minus RC. RB, I'm going to call it lowercase, just so I won't confuse. RB is equal to mm.POS minus RB, and then RC is mm.POS minus RC. That's A. I did this before, and I'm just kind of throwing myself off. Okay, now Ix is going to be Ix plus the vector xx. So xx is going to be mm dot m times r oh, this is, I don't even do that. Okay, so mm dot, it would be easier if it was at the origin, but mm dot pos minus dot x dot y. Oh, I messed this up so bad. Okay, I'm gonna stop here because I'm already too long. I'm gonna make another video where I calculate the moment of inertia and then I use that to display this. But what if you did calculate the moment of inertia as a matrix right here, you could show that this whole thing works out. You can get the angular momentum twice. And I feel bad, but because we're already 30 minutes into this, and I did this before. Let me see if I can find my previous code. Let's see, angular mass 3. Did I do it here? No, I did it right here. There it is. Okay, I did it. I'm going to show you that I did indeed do this. So there's my RCOM. There's my momentum. Here's where I calculate the moment of inertia tensor. So this is my Ix, Iy, Iz, and then I just add in this. See here, the thing here is I did move my center of mass to the origin, and that made it a little bit easier. So here's my y squared plus z squared, and then y is x times y negative, and then there's that one, and all that, and it returns a list of x, y, and z. So if you print that, you get this. And let's just run it so you can see what it looks like. So there's my moment of inertia tensor right there. Okay, you can't see that. Right there. That's my moment of inertia tensor. And then I could just operate that on my angular velocity vector to get my angular momentum. I want to do this for a rotating object in every frame, but like I said, the problem is that your moment of inertia changes each time, and you can't determine the angular velocity for a rotating object. So that makes it more complicated. I will do this better, and I will make another video, I promise, but that's that. Hope you see that the moment of inertia tensor, you need that because the moment of inertia scalar doesn't work when the object can rotate freely. That was the point. The end. I'll talk to you later.